So I'm going to, in the next 20 minutes, we are going to talk about a method to measure suspended sediment concentration that we developed for fluvial hydraulics applications and the challenge we face when we try to apply it to the coastal environment. So is this moving? Yes. Environmental monitoring is important in order to allow us to know better and more about the world that surrounds us. We are interested very much in ecological processes, in hydrodynamic processes, and for that we need to measure flow rates, water depths, temperature, suspended sediment concentration, among other variables. We also know that remote control monitoring stations are often a very good solution to allow us to take all of this data with little manpower. And of course, these remote controlled stations usually can be quite expensive depending on the instruments we put on them. Also, we know that many of these measuring stations usually are just a couple of ADCPs that are measuring velocity profiles. And we know also that the ADCPs, the acoustic Doppler current profile meters, one of its subproducts are the echo profiles. And the echo profiles, we can use it and try to relate it with the suspended sediment concentration. And that's what we are going to talk now. So to measure the suspended sediment concentration, we can use direct measurements like the optical backscatter sensors, perform physical sampling, etc. These have advantage and disadvantage. And there are some indirect methods which usually are based in sound attenuation or sound backscatter, or as we will see in a couple of minutes, in both. This method has been developed, as I said before, for fluvial hydraulics applications. We will present these methods and we will see the challenges for application to coastal hydraulics. So this is the roadmap for my presentation. First, to present the mathematical model in which all of this is founded. Then illustrate the fluvial application that we did in a river in Albania. Show where we are in migrating this method from fluvial to coastal application, and finally we will draw some conclusions. So the mathematical model, the basis is the sonar equation that we have here, where we can identify the different terms that are important to us, namely the backscatter strength, which depends on the backscatter coefficient, and the attenuation, which we relate with the sediment mass and through the attenuation coefficient. Since we are in sound, talking about sound, dB is the common unit. So if we write the equation, the sonar equation in dBs, we have this equation here, where we can find the terms already indicated. This is just mathematical processing. There is not much new of it. And if we rearrange all of this equation, where in one side we put what we know, and on the other side of the equation we put what we don't know, we find an equation that is more or less the slope, the linear equation. And on the right-hand side, we see a term which is depending on the attenuation and a term depending on the backscatter. And all of these can be then extracted from the echo profiles, as we will see. If I take the equation and I derive it, I can find a way to determine the attenuation due to the sediments, which is given by equation 2, and then that we will relate with the mass and the attenuation coefficient. Other methods based on acoustics have been used to determine the suspended sediment concentration. Some based only on the attenuation, others based on the backscatter. And in this case, we are going to use the ratio between the attenuation and backscatter. This has been proven to enlarge the scope of application of the acoustic methods. Works made in the past, namely by Guerrero et al. And Guerrero de Federico, show that the attenuation to backscatter ratio, the ABR, decreases for increasing diameters and increasing standard deviations of the sediment distributions. And all of this information can be put together for us to extract a way to, from the ABR, determine the attenuation coefficient, the zeta function. And this is basically the goal we are looking for. And from knowing the attenuation coefficient, we can determine the suspended sediment concentration. And this is the goal that we are looking for. So basically, a summary, we need to determine, we start from the sonar equation written in dB. We fit it to a linear model. We determine the parameters. The M is related with the attenuation and B with the backscatter. We calculate the ratio. And from that, and from the zeta function that we will determine based on the in an empirical calibration and on the physical properties of the sediments that we find in the site, we will obtain a function that will allow us to determine the attenuation coefficient and therefore the suspended sediment concentration. We need to measure the sediment suspended, to calibrate and to determine the attenuation coefficient. We need to know the particle size distribution and the suspended sediment concentration at certain times to correspond it to the echoes measured at that time. And usually this is achieved by means of physical sampling or other dedicated instrumentation. This function that we are looking for, it will be an empirical function and will be depending on the site, on the flow characteristics, so it will change on time. And ideally, it should be determined for a wide range of events, as we will see in the application of the fluvial case. For example, we did this for the Devil River in Albania. 7 measurement campaigns from 2016 to 2017 allow us to determine the zeta function, which we see here, that is given by a ratio of a second order polynomial by a first order polynomial, indicated by the blue thick line and the red thick line. And this is basically site dependent and also flow dependent. That's why for this case, we did a study that spanned for 2 years, 2016 and 2017. Presenting now this case study in the Devil River. The Devil is a typical mountain river in Albania, where a dam was built, and the operator of the dam had in his contract that monitoring of the river upstream of the dam has to be made. So they choose a place in a bend of the river. The middle photo is the downstream of this bridge here. This is in a bend of the river. And after this bend, the river widens a bit. But before, it's a very narrow valley where the river flows. And so under this bridge, a monitoring station composed with 2 ADCPs and the ISCO sampler was installed, and monitoring was made is been made still in a continuous way, except of course when when the water level is too low to have the ADCPs underwater. These are some images of the station. This is Massimo Guerrero and Niels Rutter installing the ADCPs. Here is the profile of the river and of the riverbed and the setup of the installation. To process all of this data and the methods, we develop a graphical user interface to integrate all of the data. So we now can do year analysis of the suspended sediment concentration, and then we can focus on the months, and then on the day, and even on hours of the flow in time. This allows us to, for instance, study detailed events like if there is a landslide, and we know that it happens in the surroundings, and give us a better perspective of the hydrology of the flow. Of course, we have the ADCP, so we can put all the data that we can gather together, like the suspended sediment concentration, the flow rate, and the water level. And with this, we can draw the hydrograph and the hydrograph curves with the water level and the discharge, and with the water level and the suspended sediment concentration. This is a work that was published recently, and that is still ongoing because the monitoring stations are still running and we are still processing the data. But of course, in science, fields tend to overlap one to another. And discussing with Professor Margaret Chan and Evelien, we came to realize that they were using ADCPs and OBSs to measure suspended sediment concentration and flow in the coastal area. And we were wondering if this method that had worked so well in a river, if we could use it in the coastal environment. And if so, what were the challenges? So we present the case study. Two field stations were implemented in Mariakerk and Gronendijk in Belgium. This is part of the PhD work of Evelien Brand. This is the type of monitoring station she had: 3 OBSs, electromagnetic current meter, 3 ADCPs. One of them was placed in the sand, and the water level to measure the probe. So this is basically a scheme of the configuration. One of the ADCPs is measuring upward, the other measuring downwards, and they are placed at a level of 70 centimeters. And the idea was, okay, let's use the data from one OBS to determine our zeta function, and then tried with the values of ADCP, try to recover the values measured with the other OBS. So in this sense, we would have independent measurements for calibration and for comparison. This is the typical evolution of the water level with time. We see the tides rising and falling, rising and falling. This is just at one of those peaks. And we select, due to the fact that the ADCPs are located at 70 centimeters above the bed, we choose only the water levels above 1 meter. These are the measurements made with the OBS, from direct measurements of sediments, suspended sediment concentration. We can see that they are very similar, which is quite nice, because when we compare one with other when considering the water level above 1 meter, we see that they fall pretty much on the y=x slope in the bisectors of the plot. And this means that we can assume that the concentration is fairly homogeneous. We then proceed to analyze the echo profiles coming from the ADCP. We try to denoise them a bit, but this is still an ongoing process, because we find some noise sources that we need to take into account. And when we fit the data, we can to the most of the profiles, the fit is quite good. We have R-squareds of over 0.9, 0.95. And then we determine the sediment attenuation by the method shown before, which seems also very reasonable. But when we compute the attenuation coefficient, this zeta function, we see that the data is grouped more or less in a thick cluster of points. And this, for us, if we compare it with the previous, and I should have put it here, when we compare it with the one we obtained for the devil, which is spread all around the plot, and it's a nice function, this caused a bit of a perplexity. We were not expecting that. So we decided to analyze what's happening in this cluster of points. Of course, the first thing we did is probably this is somehow related with the cycles of the tides. So we decided to take 3 cycles and divide them in the rising tide and on the falling tide, and try to see what's happening to these points and how can we find some monotonous continuous function that we can fit to the data. And this is still the ongoing process. So for the peak one, we see that during the rising, the red points are clustered in a region, and the falling tide, they cluster on a different one with small overlap. But for the second peak, there is almost a complete overlap between rising and falling. And for the third peak, this overlap still persists, but the shape is different. So this is what we are doing now, and we are trying to investigate what is the physics, what is the meaning of these results. One of the ideas that are now under testing is choose only fits with I r square, and for this means r square over 0.95. And another thing that we do is that we are time averaging the profiles every minute, and probably changing the average window to see what we can, what is the immediately change that we can see on the distribution of points. I'm finishing my presentation. So we present a mathematical model used in fluvial hydraulics to determine the suspended sediment concentration from the echoes profiles from ADCPs. This basically, we determine the attenuation to backscatter ratio by fitting the Sonnet equation to the echo profiles. We know this was successfully applied to a fluvial case study. Actually, it was 2, one in Italy, one in Albania. Now we are in the process of applying it to a different field in coastal area, and these are the challenges we are facing. So if you have any ideas that we can discuss, I would be very glad to discuss them with you. This is the references quoted during the presentation, and I hereby conclude this presentation. Thank you very much.